The Milky Way galaxy is an expansive giant, home to hundreds of billions of stars and at least 100 billion planets, many of which shine brightly in our own night sky. But there are others hiding in plain sight. If we gaze at the stars hard enough, we can even get lucky and catch a glimpse of the fleeting remnants of solar system bodies. What are these near-Earth objects, and could they have played a role in our evolution?
I look at these objects as tracers of the very earliest stages of planet formation in the solar system. We can study the planets and try to understand how they formed and evolved, but the planets are complicated bodies. They have weather and wind, they have water, they have plate tectonics in the case of the Earth, they have volcanism. All of these things act to erase and reset the surfaces of the planets, and that makes it very difficult to learn about how the Earth formed 4.5 billion years ago. In contrast, the asteroids are leftover fragments of the planet formation process and have been sitting out in the solar system for the past 4.5 billion years, relatively undisturbed. And so by studying these objects, we're really able to peer back into the past and understand what the conditions were like as planets were forming, both chemically and physically. So we have 600,000 of these things to study. We can't send spacecraft to all of them, but we can use telescopes here on Earth. For a long time, the traditional definition of an asteroid and a comet is that an asteroid's a rocky body, and a comet's an icy body that shows activity, a coma, jets, a halo, those types of things that we associate with the comet. In the past 10 or 15 years or so, we've started to discover asteroids that, for whatever reason, all of a sudden turn on, just like a comet would. They start to show activity, they start to show evidence of outgassing, loss of volatiles, loss of dust, just like a comet. And we now think that there are quite a few processes probably responsible for taking some of these objects that we would have classified as asteroid and turning them into comets. Collisions is one possible way of making an asteroid look like a comet. If you have an asteroid and you collide a body onto its surface, that's going to kick up a big dust cloud. And as viewed from Earth, we will see an asteroid with a big dust cloud around it that looks just like a comet. They can be a hazard. I mean, we certainly know that near-Earth asteroids can and do hit the Earth. We have numerous pieces of evidence all over the Earth in the form of impact craters that, in some cases, very large objects have hit the Earth, and we think that there's a pretty good correlation between extinction events and impacts from asteroids and comets. Well, the most famous being the impact that potentially killed off the dinosaurs. We have evidence of that impact off the coast of the Yucatan Peninsula in Mexico. But there are numerous others throughout history that we think correlate with extinction events that we see in the fossil record. With that said, though, those events are exceedingly rare. And they're so rare that I don't stay up at night worrying about the next killer asteroid coming along.
While impact events here on Earth are few and far between, parts of asteroids and comets have reached our planet in the form of meteorites.
There's a whole host of terminology associated with meteors. There's meteors, there's meteoroids, there's meteorites. Meteors come from a variety of sources. Some of them are particles that have been released by comets. Some of them are dust particles released by asteroids, generally formed through collisions. So when two asteroids collide, you produce a shower of fragments. Some of those fragments can make their way to the Earth. Before that passage through the atmosphere, you could refer to that particle or that rock as a meteoroid. If that meteor makes its way to the ground, then that is when it becomes a meteorite. Generally what happens with meteorites is that they will impact the atmosphere, and as that body passes through the atmosphere, it undergoes extreme heating and fragmentation events, and it fragments into many pieces, and those pieces get scattered all over what we would call a strew field. Those pieces can range in size from little dust particles all the way up to large blocks, and the biggest meteorites in the world can be the size of rooms. In February of 2013, over Chelyabinsk, Russia, a modest-sized meteoroid or asteroid hit the atmosphere, passed through the atmosphere as a meteor, actually blew up at a relatively high altitude and showered down fragments of that material onto the surface of the Earth. That was not predicted, and part of the reason for that is that it was a relatively small object, about 15 meters in size or so. Something that small is hard to detect with ground-based telescopes. But perhaps more importantly is that it approached from the direction of the sun. If something of that size is coming from the direction of the sun, we're not going to know about it ahead of time unless it's been discovered years previously. This amazing fireball, this streak of light, appeared in the sky. It left behind a vapor trail or a gas trail, and people ran to their windows to look at this. Several minutes after the fireball, the shock wave from that event made its way down to the surface, and that shock wave blew out windows all over this region in Russia. And it was the shattering of windows onto people's faces that were looking out the window that caused the greatest amount of injuries in that event. So it wasn't necessarily that there was a large impact crater and flash heating or anything like that. It was the shock of the fireball. This is actually a relatively small piece. The largest piece that was recovered was maybe 0.5 meter in size. It was actually at the bottom of a lake. This is actually what we would refer to as an ordinary chondrite, which is, unsurprisingly, a fairly ordinary meteorite. It's the most common type of meteorite that falls on the Earth. About 80% of all meteorites fall into this category. Well, this meteorite itself formed about 4.5 billion years ago in the solar system and has been floating around in space since then. It probably lived part of its life on the surface of a main belt asteroid. At some point, that main belt asteroid was probably impacted and fragments were removed from that surface, and those fragments then made their way to Earth. It impacted and delivered the meteorites to the ground. So there's nothing terribly extraordinary about it, except for the fact that it has a very specific and very well documented impact event associated with it, which is fairly unusual. Most of the time these things fall in remote regions where people don't witness the falls, but this is the most documented impact in history. This is one of the more popular type of meteorites. It's called a palisite. This is a mix of gem quality peridot or olivine in a matrix of metal. And so it's a really striking, beautiful piece. And we think that something like this probably formed around the core mantle boundary of a large protoplanetary body. So just like the Earth has a core, a mantle, and a crust, we think planetary bodies out in the solar system, some of them may have undergone that similar differentiation process. And so this is a chunk of a core mantle boundary of one of these differentiated protoplanets. And obviously that protoplanet has been disrupted so that it has been collisionally fragmented into a piece that we have now collected as this meteorite. Many of them are cut into these slices so that you can see the sort of appearance and internal texture of the meteorite. The last piece here that I'll show is a fascinating meteorite. This is an iron meteorite. This is a slice of the iron meteorite. Its surface has been etched so that you can see this crystallized, interleaved pattern of crystals on the surface of it. This particular iron meteorite has the oldest date of any rock in the solar system, and that's 4.567 billion years old. And this rock was probably the first thing that formed in the solar, the first planetary body that formed in the solar system 4.5 billion years ago. And there's a really interesting history about how we think something like this could have formed so quickly. It requires very rapid accretion, so the body accreted very quickly. And because we're looking at an iron, this is a chunk of iron nickel metal, this is almost certainly the core of a differentiated body. So you're looking at rapid accretion and differentiation in the first few million years of solar system history, which is staggering to think that such complicated geologic processes were happening so early in the solar system. And it was those bodies that this meteorite represents that were the precursors to the Earth and the planets in the solar system. So it was objects like this that were colliding and sticking together that ultimately formed and built up the planets. So by studying these objects, we can understand the building blocks and the ingredients that went into form the Earth and set up the conditions that makes the Earth habitable and sustainable for life.